Let's look at an example of a maximization or a minimization problem involving an objective function with more than one choice variable. So let's start off with z equals some function of x and y, and it's equal to 3/2 x squared plus 4xy minus 13x plus 7/2 y squared minus 19y minus 12. So what we have to do is find the critical values of x and y that lead to a stationary point of this on this objective function. So looking at our first order necessary conditions for a max or min, we know we have to look at all the first order partial derivatives of our objective function with respect to each choice variable and set those first order partial derivatives equal to 0. So let's do that right now. We're going to look at the partial of f with respect to x, and our notation is just fx, and that partial derivative will be a function of the same variables that the original objective function was a function of, x and y. So let's just try to keep everything in order here. And what is that partial derivative equal to? Well, term by term, it's equal to 3x plus 4y minus 13, and set that first order partial derivative equal to 0. And then we also have to look at the partial derivative of our objective function with respect to the next choice variable y, and set it equal to 0 as well. So fy, and it will be a function of the same variables the objective function was a function of, x and y. Let's keep everything in order here. And fy will be equal to, term by term, 4x plus 7y minus 19, and we need to set that equal to 0 as well. So now if we look at our first order necessary conditions here, we have a system of simultaneous equations involving the two choice variables, x and y. So how can we solve this system of equations for x and y? Well, we could use Cramer's rule. So we need to set up our A coefficient matrix, the x variable matrix, and the D matrix of constant terms. When we do this, the A coefficient matrix would contain the coefficients of the variables x and y, 3, 4, 4, and 7. The x variable matrix would contain the variable x, which is our first variable in the first column, and then x is our second variable. And our D matrix of constant terms can be derived once we take the constant terms in each equation over to the right side of the equality. So we get a 13 from the first equation and a 19 from the second equation. Okay, now to use Cramer's rule to solve for x and y, we need the determinant of the A1 matrix, the determinant of the A2 matrix, and the determinant of the A matrix. So here's what we're going to get. X, the first variable in our x variable matrix, is equal to the determinant of the A1 matrix over the determinant of the A matrix, and the determinant of the A1 matrix. What are the elements going to be there? Well, in the first column, we use the D column vector 13 and 19, and then we use the remaining elements of the A matrix. And the determinant of the A matrix is the determinant containing the elements 3, 4, 4, and 7. So when we evaluate this, we get, let's see, 13 times 7, which is 91, minus 4 times 19, which comes out to be 76, all divided by the determinant of A, which comes out to be 5. And this comes out to be the number 3. Solving for y is going to be the determinant of the A2 matrix over the determinant of the A matrix using Cramer's rule. So when we form the determinant for the A2 matrix, the elements in the first column will be those from the A matrix, and then we simply fill in the second column with the D column vector 13 and 19, all divided by the determinant of the A matrix, which we know is 5 from before. So when we solve this, it comes out to be 3 times 19 in the numerator, which is 57, minus 4 times 13, which comes out to be 52, all divided by 5, and that comes out to be the number 1. So we now have a critical value of x and a critical value of y, and if you were to put that back into the objective function, you would get a stationary value of z, and our stationary point on this function would consist of the coordinates x0, y0, and z0. Now the question is that stationary point on the objective function a maximum or a minimum? So now we need to look at our second order sufficient conditions for a max or a min. And we showed that to do this, we need to look at the Hessian determinant or the Hessian of our objective function. And the symbol for that is H, surrounded by the bars for the determinant symbol. And the way we get the elements for this Hessian determinant is this is the Hessian determinant of our objective function, and the elements of the Hessian are second order partials of the objective function. How can we remember the order of these second order partials? Well, go back to our first order necessary conditions. And if we were very careful in how we describe those first order partial derivatives, fx, fy, as functions of x and y, the order in which they appeared in our objective function, the second order partials are easy to get. For the first row of our Hessian, we're going to look at fxx and then fxy. And for the second row of our Hessian, we're going to go fyx and then fyy. So let's just fill in those elements. We get fxx, fxy, fyx, and fyy. And of course, fxy and fyx should be the same because of Young's theorem. So let's see what these elements come out to be. Well, if we go back to our earlier work, fxx, the partial of fx with respect to x is 3. So let's put in that number 3. fxy, the partial of fx with respect to y is 4. fyx, the partial of fy with respect to x is 4. fyy, the partial of fy with respect to y is 7. And we know that that second order determinant comes out to be 3 times 7 is 21, minus 4 times 4 is 16, which comes out to be 5, which is positive. Also, we need to look at the successive principal minors of this Hessian determinant. We need to look at the first principal minor of the Hessian, which is a subdeterminant of the Hessian, which contains the first element along the principal diagonal. So it's just going to be the determinant of fxx, which in this case comes out to be the determinant of 3, and the determinant of a scalar is just the number 3 itself, which is positive. We also know that the second principal minor of our Hessian is a subdeterminant of the Hessian, which contains the first 2 elements along the principal diagonal. So the second principal minor of the Hessian will just be the Hessian itself, and we already know that's equal to 5, which is positive. So what can we now conclude? We know the first principal minor of our Hessian is positive, and the second principal minor of the Hessian is positive, which implies the second order differential of z is going to be positive for all values of dx and dy not both 0. And if that's the case, this implies we have a minimum. We have a minimum of our objective function, or a minimum of z, which is some function of x and y, at the critical values of x and y at x0 equal 3 and y0 equal 1.